Hello and welcome to our lecture on damped simple harmonic motion, which also includes damped driven simple harmonic motion. So what are we talking about here today? Well, this is our last lecture on oscillatory motion, and it's really the kind of leftover topics. It is also the tip of an iceberg because these are very big topics with rather complex solutions and complex forms of their functions that you can spend a whole semester discussing. Furthermore, these are ideas that you will see more fully explored in an introductory physics multi-semester sequence when circuits are discussed, specifically oscillating circuits called LRC circuits. But we're not talking about that today. Here we're talking about actual mechanical oscillators, and these are very much the springs with the attached masses that we've seen before. But there's one important difference. Now we're acknowledging that these springs with attached masses experience a dragged force and have a damping coefficient. And that means that over time, the oscillation will stop. Because just like in the real world, if you set a spring oscillating, gradually it will slow down and come back to rest on its own, because it will lose mechanical energy to heat and sound energy in the environment. Okay, so let's take a look at the t terms and eventually the mathematical forms of these different types of motion. Okay, so first of all, let's get the idea of the exponential decay envelope out of the way. Well, here it is in the picture, okay? And what it represents is it's the secondary function that determines the time-dependent decay of the amplitude of the oscillation. Because notice here, this is an oscillation, a simple harmonic oscillation, right? This right here would be one full period, since the horizontal axis is time, that'd be a period. And the period isn't changing much. We'll actually see that there is a slight change to the period due to the damping, but it's very small and it is constant. So this would just be a different period as compared to a purely simple oscillator that didn't have any damping at all. But the thing that's new is that each subsequent amplitude is smaller than the last, because the oscillation is exponentially decaying to rest. Okay, so we call that the decay envelope. All right, well, what brings this decay envelope on? Well, that's some sort of damping force and a damping constant that's associated with that damping force. So it's a non-conservative force. That means it's removing mechanical energy from the system, and it causes the amplitude to decrease with the form of, well, Stokes drag, which is drag force equals negative BV. All right, so this is also called linear drag as opposed to quadratic drag or Newtonian drag. It's the simpler form of drag and is the type that actually gives us a well-defined solution and basically a function or a position function that we're going to see in our key equations. Okay, and the damping constant is B. Okay, and that would have the appropriate units to make this a force equation. So if we have over here kilogram meters per second squared, then over here we're then going to have kilograms per second times meters per second. All right, so the damping coefficient we can see has units of kilograms per second, mass per time. All right, so that is our decaying oscillation. Now, it turns out that you can have oscillations decay in different ways. You can have oscillations that are called underdamped, and this is an oscillation that's starting, say, at full amplitude. Underdamped are ones that are basically like in the picture shown above, where they're going to oscillate a few times before they eventually come to rest. You can also have what's called critical damping, okay? Then you can also have something that's too damped, so it's going to basically take a almost infinite amount of time to eventually reach equilibrium. It's going to be very slow in its approach. Okay, so those are the three types of damping, and we can actually explore those a little bit. So I'm going to zoom in. I have it quite small here. So three types: type A, underdamping; B, critical damping; and C, overdamping. And we can see it's all about the relationship between the damping coefficient, that's measured of course with units of kilograms per second, and the spring constant and the mass. All right, so it turns out, right, we're not going to prove it here, but with overdamping, okay, then you have a case where you have the damping coefficient squared is much larger than 4 times the mass times the spring constant. So the spring just isn't springy enough compared to how much drag force there is, and this results in no oscillation and a very slow approach to the equilibrium, which is really a return to equilibrium. On the other hand, critical damping is where B squared the damping coefficient squared is exactly equal to 4 times the mass times the spring constant. This also results in no oscillation, but it means that we reach equilibrium in a minimum amount of time. So it's kind of funny to talk about an oscillating system that doesn't oscillate, but of course that is actually something you want. And really the best illustration of critical damping, the one that always comes to mind, is what's called the dash pot, which is the thing that is above doors that allows the door to close slowly. It is a hydraulic basically device, and it allows the door to not slam shut but close slowly. All of our campuses have them, right? And so that is an example of, if it's well made, of a critically damped oscillator, because the door closes slowly but not too slowly, and it doesn't just slam shut and then bounce against the door frame. It closes nice and evenly. Okay, so that would be a critically damped oscillator. On the other hand, underdamping is where the damping coefficient squared is less than 4 mK, and this results in leftover oscillations. Okay, so you still have that decay envelope, but there's definitely going to be some few true oscillations. Okay, and then I kind of sum things up a bit over here. Damping can change the time-dependent decay of the oscillation, and critical damping returns the oscillator to equilibrium in the least time. And that's really the one we care about for engineering purposes. So speaking of engineering, we also have a very interesting idea, and that's the idea of resonance. And this has more to do with a driven oscillation. Now, when we talk about driven oscillations, mathematically it turns out we always will have damping, because otherwise if you drive a simple oscillator where you're ignoring the real-life application of damping, then what happens is when you hit resonance, you have an infinite peak amplitude. And that makes no sense. You can't have an infinite amplitude. So when we actually talk about a driven system, we're always including the same damping that we talk about in a non-driven damped oscillator. Okay, so resonance is, it results in max amplitude, and it occurs whenever the driving frequency, the angular frequency, approximately equals the natural frequency. Because it turns out that everything that can oscillate has a natural frequency. If we think about the natural frequency of a spring, then it's just going to be equal to K over M. All right, that's the natural frequency, angular frequency of the spring. Okay, and we can model a lot of mechanical systems as some sort of combination of springs, or at least simplify them as a combination of springs. Okay, and one direct related value to resonance is something called the Q value. And it's one quantity. Q value really stands for the quality factor, as we see here. It's one quantity that describes the following characteristics of the amplitude curve. As we can see, we have different cases of Q values resulting in different shaped curves. Here we have curves that are getting progressively steeper and with a higher peak. That would be the resonant peak right there, where and we can tell it's the resonant peak because the ratio of the driving frequency over the natural frequency is 1. Okay, so that's exactly the condition for resonance. Okay, but different Q values will relate in different shaped peaks, and even more on a more refined level, they result in different shaped peaks, and also the peaks themselves can shift a little bit relative to the natural frequency. So we can see as the Q value becomes larger, we have better alignment between the driving frequency, creating maximum amplitude exactly at the natural frequency, whereas where the Q value is an intermediate value, you can see the peak is slightly off, and where the Q value is very small, there's really almost no discernible peak at all. And indeed, these correspond to Q values for a particular oscillator of 6, 2, and 0.71 for A, B, and C, respectively. Okay? So we can really see there's a lot in the Q value, and it relates to the location of the peak, the shape of the peak, and the height of the peak. But most importantly, the simple idea, the takeaway, is you want to think of large Q values mean taller and steeper resonant peaks. And so if you want a system that is really able to resonate well, if resonance is important and desirable for a system, then you want to have a high Q value. On the other hand, if you don't want something to resonate in an undesirable way, like a car that hits a particular frequency and starts shaking itself apart, then you might not want to have a high Q value, and you might want to design that into the system. Okay, so here are all our key formulas. You see we have quite a few of them, a whole page of them, and that's basically because there's a procedure here. We consider the new force, then we include the new force in Newton's second law, then we rewrite Newton's second law to turn it into a differential equation, and then, because this isn't a class that requires knowledge of differential equations, then we propose a solution that indeed works, and then use that as our new position function, okay? And that's why it takes a lot of space in terms of the key formulas. So let's just move right through these, okay? So the first one here is none other than the damping force, okay? So the damping force is proportional to velocity. It's basically a drag force. So then if we include that in Newton's second law, now we have the spring restoring force plus the drag force equal to mass times acceleration. If we rewrite this, we get an equation of motion. All right, so this is the equation of motion for the simple damped oscillator. This is a differential equation, right? Obviously, it's more complex than the differential equation for the undamped simple harmonic oscillator because we've got a whole new term. Now, if we solve that differential equation, the solution to that equation is this right here. We can see that it looks very similar, at least on first pass, to the position function for the undamped simple harmonic oscillator because it has a cosine in there. But look, it's got this other function right in front. It has the exponential decay envelope, okay? And the power of the exponential decay is b over 2m. We can replace that with something called gamma, all right? It's just kind of a mathematical convenience. It's just labeling that this is the position function. Notice that notation, right, or that terminology. The equation of motion is the differential equation that comes from Newton's second law. The solution to the differential equation is the position function. Okay. Now, of course, we could take the derivative of this and get a velocity function, but here we'll stop at position because we already have a lot of information. Okay. All right. So this is just pointing out that gamma is simply a cleaner way of writing the position function, but it's the way you'll often see it expressed. Now, notice we also have omega prime, not omega. Well, it turns out that when you are testing that this proposed position function is indeed a solution to the differential equation and proving that it's true for all values of time, you're left with an interesting constraint on omega, just like the constraint that's left for omega in the undamped simple harmonic oscillator, which gave us that omega is just the square root of k over m. But now we end up with a second term inside the square root. So this right here is the damped angular frequency. What is interesting, though, is that this damped angular frequency always, or almost always, ends up being very close numerically to the undamped angular frequency. And that's because the second term here, this b squared over 4m squared, is almost always a much, much less than 1. So it's such a small number that it doesn't really affect the square root very much. And we can also approximate the energy in a damped simple harmonic oscillator as this formula here. Okay? All right, so that's the damped simple harmonic oscillator. Now let's look at the driven damped simple harmonic oscillator. We're now just adding another force to Newton's second law, and that's the external driving force. That would be, maybe it's like you physically shaking something. It could be an earthquake. It could be other natural driving forces. It could also be mechanical forces like in a factory or something that are external to the thing that can oscillate, the spring, okay, or the approximation of a spring, okay? And so that's where they're acknowledging here that the external force is F naught times cosine omega d times t. Omega d is the angular driving frequency, okay? It's just 2 pi times the external driving frequency, which would be the non-angular, that right there, would be the non-angular driving frequency, okay? All right, so then that allows us to come up with a new equation of motion. The way we write it, unlike all of our other differential equations, which are our equations of motion, we're not setting it equal to 0. Instead, we're setting it equal to the driving frequency. And it turns out the solution to this differential equation is even more complex. It's got two terms, right? It's got an initial term, and then it's got a separate term. Now, it turns out that this term here is the one that is a consequence of the fact that we did include drag. And if we hadn't included drag, there actually would have been no solution to the differential equation. But this second term here ends up going away after a few seconds, or often a fraction of a second. So for prolonged driving oscillations, we can approximate the position function as just a naught cosine omega dt plus the phase angle. But notice that something really interesting has happened, that as we test this solution, the amplitude itself is dependent on the frequencies, and the phase angle is dependent on the frequencies. And this is a level of mathematical complexity that we haven't seen before with other differential equations. And indeed, we won't test this, but we see then that the actual amplitude of the driven damped simple harmonic oscillator is this here, dependent on the driving force, the driving frequency, the natural frequency, and the damping coefficient, as well as the mass. The phase angle also is dependent on many of the same terms, except the force doesn't show up in it. Now, it turns out that we can estimate we can point out that here the natural frequency is technically actually the damped natural frequency, but for all intents and purposes, we could just approximate it as the square root of k over m. And then finally, here we have the Q factor. The Q factor is graciously a very simple expression, and it just gives us that Q is equal to the mass, the natural frequency, divided by the damping coefficient, okay? And this Q factor, though, is only really relevant for driven oscillations, okay? But it's not dependent on the actual driving force. Okay, well, there we have it, right? Our quick view, our brief introduction to damped simple harmonic oscillators and driven damped simple harmonic oscillators. I have two simple examples because this is mostly kind of a concept lecture where the examples that are actually related at this level in this class are rather simple. So let's just run through our two simple examples and wrap up this lecture. So for practice, example 1. For a damped oscillator with a mass of 1.349 kilograms, a spring constant of 110.5 newtons per meter, and a drag coefficient of 1.722 kilograms per second, what is the period of motion, the length of time it takes the amplitude of the damped oscillation to drop to half its original value, and the length of time it takes the mechanical energy to drop to half of its value? Okay? All right, so let's go ahead and work this out. Okay, so first of all, we're going to find the damped frequency, which ends up being 9.03 radians per second, and that's just plugging into the formula that we were given. All right, and this is very, very similar to the undamped natural frequency of the oscillator, or we here might as well just call it the frequency, because here we can see it's 9.05. So indeed, as I said before, the numbers are very close, although they're different by less than 1%. Okay, and then we want to find the, or relate the angular frequency to the period, like so. Okay, and then, excuse me, then we can solve for the period, and it ends up being 0.696 seconds. Okay, so that's the length of time it takes the amplitude, or excuse me, that is the period of motion. Now to find the length of the time, we're going to focus on just the exponential decay part. So we need only look at the decay envelope, because we don't, basically, we don't care what the kind of the time-dependent behavior is. We just care when the amplitude is going to fall off. Okay, so the cosine part, the actual oscillatory trigonometric part, is not important if you're asked a question about decaying amplitude. Okay, so essentially, I'm just going to look at this equation here and just solve for t. Okay, which is kind of neat because we just get to isolate it outside of the exponential. So we'll take the natural log of both sides, which gets rid of the e raised to the power of negative b over 2m times t. Now it just becomes that, and then we just continue to we just continue to isolate t like so. And there we go, and we get 1.086 seconds. That's how long it takes it to decay to half its original amplitude, okay? And obviously different masses and different drag coefficients will give us different values. And then finally, in part C, how long does it take the mechanical energy to drop to half its original value? So here we set up, we acknowledge that this is the working approximation of the total mechanical energy in a decaying simple harmonic oscillator. And we're just going to set that equal to 1/2 of its original value, okay, because this is the total energy in the system when it starts off, because it's starting off entirely as potential elastic energy, okay, right? And then we just go ahead and solve for t, and that's what it looks like once we simplify it, and we get that it's 0.543 seconds, okay? So the energy decreases much faster than the amplitude. Okay, all right, example 2. A 1,000 kilogram car carrying 4 82 kilogram people travels over a washboard dirt road. You know, the type with lots of bumps that are evenly spaced apart. All right, so the corrugations in that washboard board are 4 meters apart, so that would be their wavelength. The car bounces with a maximum amplitude when its speed is 16 kilometers per hour. When the car stops and the people get out, by how much does the car body rise on its suspension? So this is kind of neat because we're going to use this driven frequency to relate it to the natural frequency and then go from there. All right, so first of all, we're going to find the total mass of the car, which is 1,000 plus 4 times 82. And then we're going to go ahead and find the natural frequency of the car, all right, with this simple formula here, okay, because we're kind of treating it as undamped, but again, that's a pretty fair approximation, okay. And by definition, omega is 2 pi over t, all right, so then we can replace omega with 2 pi over t, and then go ahead and then acknowledge that the period of the bumps is determined by the velocity and the spacing. All right, so then we know that the period of each bump, when the car is traveling at 16 kilometers per second and the bumps are spaced 4 meters apart, means that the period of each bump is being experienced by the car at a rate of 1.11 seconds. And so then we can go ahead and plug that back in and then solve for the spring constant. See? And once we have the spring constant of the car, then we can simply find out how much the car was compressed by the passengers within, and then go ahead and then solve for how much the car will uncompress, and it will lift up by 7.8 centimeters. So it's not using many of the ideas that were presented, obviously, with the driven harmonic oscillator, such as all the the complicated the amplitude and the amplitude's dependence on the frequency and so on. We also didn't solve for a Q value here, although a Q value would be a good example of the type of problem you see for a driven harmonic oscillator. This is rather just a brief introduction to the idea. Well, but regardless, I hope seeing the equations and seeing how we all have these differential equations with different solutions to them, being the position functions, has been very helpful, informative, and interesting. And I appreciate you watching this lecture video.